Okay, now, for some of the weirder limits, let's take a look at these. These are the so-called indeterminate forms. If you ever get infinity over infinity, or 0 over 0, what the heck is going on? I'll give you, for instance, lim. As x goes to, say, infinity, 3x plus 1 over 2x minus 5. Okay? At first blush, you're going, well, what I've got is, if I plug in infinity, I get 3 times infinity plus 1 over 2 times a huge number minus 1 is really a huge number over huge number, and it's anybody's guess. But you guys already know how this goes. You could hit this with a 1 over x, right? And end up ultimately with, 3 over 2. You can do the work yourself. So here I had infinity over infinity, and yet it seems like you don't know what to do, and yet you have an answer 3 over 2. The same can happen with 0 over 0, infinity over infinity. The rest of these guys, they seem so, like some of them look like, well, 0 times anything is 0, isn't it? No, it's not equal to 0 generally. Surprise! Infinity minus infinity, isn't that 0? Tug of war, right? Nope. We don't know. We have to test them. 0 to any power is 0. Infinity to the 0. People go, this is 0. This is 1. You know what? We don't know. And there's others. There's strangeness here. Okay? So what we need is a tool to unlock it. It's called L'Hopital's rule. It was published by L'Hopital, but history tells us that one of the Bernoullis, the fabulous Swiss family, the Bernoullis, came up with this and gave it to him to publish. Anyway, what it says basically, surprise, is that if you've got, this is important, it has to be, if you've got this strange infinity over infinity or 0 over 0, right? And you're looking for this limit, when you take this limit, x goes to a and you get f of x over g of x, and you get one of those forms, then this is what you can do. The limit as x approaches a of f of x over g of x is identical to the limit as x approaches a of f prime of x divided by g prime of x. In other words, the limit of the functions is equal to the limit of the ratio of the functions is equal to the limit of the ratio of their derivatives. Let's write that out. The limit of the ratio of the functions, okay, the functions is equal to the limit of the ratio of the derivatives. You want me to prove it? Neither do I. Watch this. Actually, we'll do it first of all on this one, then we'll look at some strange examples. So we'll look at this right now. In fact, let's put it down here. Bonus problem. Limit as x approaches infinity of 3x plus 1 over 2x minus 5. As we saw above, this goes to infinity over infinity. In that case, we are allowed to use L'Hopital. Okay? So L'Hopital, or L'Hospital, the hospital, whatever. That's his name. Spell check always spits it out at me. What the heck did you write there? It's L'Hopital's rule. Anyway, L'Hopital's rule says this. I put a little symbol. I'm going to use it. Equals lim. Now watch out. Nice and slow. First time. I'm going to do it this way. Take the derivative of the top and divide it by the derivative of the bottom. Now you guys are great students and you're very conscientious, but you'll kind of read this as like, oh, at first your mind will go, oh, I've got to do quotient rule. Not here. This is L'Hopital's rule, not quotient rule. And he says derive the top separately. So we take lim as x approaches infinity. Derivative upstairs is just 3, isn't it? Derivative downstairs is just 2, isn't it? That's just a number, isn't it? As x goes to infinity, that number is just a number. And again, we get 3 over 2, okay? Now, personally, if I'm faced with this guy, I just look at the lead coefficients and that's my answer, if the powers match. But this thing helps us with a ton of different problems. Let's take a look at a few more. Okay, here's one. The limit as x approaches infinity of 3x squared plus 2x over 1 minus 4x squared. Okay, what I'm getting here is it's approaching, obviously, if you put in huge numbers, upstairs you get huge numbers over huge numbers. So once again, L'Hopital to the rescue. So it's equal to the lim, and if you don't mind, this time I'll just derive the top. Okay, the top derived is 6x plus 2. The bottom is negative 8x. Okay, you can go fun and games with that, but I'm going to show you something else. If you put in infinity, you get infinity over, do you see how you get negative infinity downstairs? Regardless of the sign, it's still an infinity, a huge number divided by a huge number. And you know what? I'm going to run L'Hopital's again. You can do that? Yes, you can. It's equal to the lim. I'm showing you new stuff, aren't I? X approaches infinity of 6 over negative 8 is, it's negative 6 over negative 8, or negative 3 over 4, and that's that guy's limit. Now with rational functions, you can kind of see it, can't you? Negative 3 over 4. Okay, but other functions, check this out, not so much maybe. So as x is approaching 0 from the plus side, we have sine x over x. If we plug in 0, we get sine 0 over 0. Sine of 0 is 0 over 0. It's not 0. It's indeterminate. We don't know what it is. But L'Hopital comes in and helps us out. L'Hopital says this is the same as the limit as x approaches 0 from the plus. Derive sine, you get cosine. Derive x, you get 1. Can we plug in now? You see how the bottom is 1? L'Hopital is out now. It's either infinity or 0. You actually have an answer now. When you plug in 0, you get cosine of 0 over 1, which is 1 over 1, of course, is 1. And that's actually, we've done that limit before, but in a different way. There it is. L'Hopital's handles it easily. All right, the rest of these, and I think I have 1, 2, 3 more examples, and I need to go through them with you guys. I'm going to show you other techniques, okay? All right, so bear with me now. All you have to do is, the game is really, let's get this in the form that L'Hopital can handle. Right now, if we look at this and plug in, I've got x, I'm going to negative infinity. So it looks like what we've got here is x is negative infinity, and then natural log of 1 minus 1 over negative infinity. Okay, so that's the same thing as negative infinity. This I know is 0, 1 over infinity. So I really am looking at natural log of 1, and natural log of 1 is 0. So I've got this weird case of what the heck is this itis, right? I've got minus infinity times 0. That's one of the stranger types that I kind of pointed out to you way up here somewhere. Way up here. So far, I'm tired of looking for it. Not that far. Okay. It's this one, isn't it? Okay. Okay, I got to be gentle with Microsoft Word. It keeps on wanting to die on me. So what do? I want to make it look like, you know, L'Hopital. Ready? Algebra. This is equal to lim. X approaches minus infinity. I'm going to leave natural log upstairs, 1 minus 1 over x. But I'm going to bring the x down as 1 over x. What do you think about them apples? What happens upstairs, we found, remember we did all that? He's still 0. Downstairs, you have 1 over infinity, right? Negative infinity. And now you got 0 over 0. This actually starts making you happy because it means you get to use L'Hopital. So we're going to use L'Hopital on this guy. That means we're going to take lim as x approaches negative infinity of, now back up. This is important. If you get 0 over 0 or infinity over infinity, you get to use L'Hopital's rule. What made me put the x down there? Experience, just experience. It's easier to flip x over down below than it is to mess with natural log. So that's what I was thinking when I was doing it. Okay, so we're going to derive the top. The top derives as 1 over 1 minus 1 over x. And then we're going to go the derivative of, what, minus 1 over x, right? Downstairs is the derivative of, well, let's do the derivative. We kind of know that, don't we? Let's just do it. So the derivative of the inside is negative, and then it's going to be x minus 1. So it's going to be another minus 1, x to the minus 2. And downstairs, you're going to get a negative x to the minus 2. Okay, so we have lim, x approaches minus infinity. We've got 1 over 1 minus 1 over x, and a double negative, and we've also got 1 over x squared. Downstairs, guess what? Negative 1 over x squared. You see that? Yeah, that's some heavy-duty deriving right there. We can, at this stage, cancel these guys. Still the negative is surviving, and we can actually take this guy's limit now. We've got lim, x approaches negative infinity. We've got a negative to put somewhere. How about there? And we've got 1 over 1 minus 1 over x. And you let x go to infinity, and you know what happens to this guy, don't you? Plus or minus infinity, he goes to 0. Our final answer looks like it's negative 1. What do you think about that? Crazy. In the next case, you could have paused it right there. You see I paused a little for drama. You can pause it there and look at that and study it. We're going to go into another one. This one, if you are letting this guy go, we're getting 1 over 0 minus 1 over tan inverse of 0. Well, I'm glad you know your trig, because that's really 1 over 0 minus tan inverse of 0 is 0. So we're getting infinity minus infinity. Egad. What do we do? You ready? Algebra. We'll write lim as x approaches 0 from the plus, and we're going to write it as a common denominator. That's right. X tan inverse of x, tan inverse of x minus x, and now we plug in, and what we get if we do that, I hope it's L'Hopital, we have tan inverse of 0 minus 0 over 0 times tan inverse of 0. You know what? Yeah, this thing is going to 0 over 0, and L'Hopital is going to save us again. We're actually doing some really highfalutin problems here, and it's good to see them. So this might be a video you watch more than once to see how this goes. Okay. All right, we got to wait for Microsoft Word to do its thing. There we go. So now we're going to go L'Hopital. All right, so we have lim as x approaches 0 from the plus, derive the top, and remember what tan inverse is, 1 over 1 plus x squared minus 1. Derive the bottom, oh my gosh, a product rule, 1 times tan inverse of x plus x times 1 over 1 plus x squared. And I hope that this is going to go well. Let's see what happens. Upstairs we're getting 1 over 1 plus 0 squared, which is 1 minus 1, so the top is going to 0. Okay. What's the bottom doing? I've got 0, so I've got tan inverse of 0 plus 0 times I don't care. We still get 0, don't we? Oh my goodness. Well, you know, we got to be maybe a little more resilient here and wait for this thing to be able to scroll. One thing I'm thinking I could do is, it's a complex fraction, so maybe what we can do, there you go, is multiply top and bottom by, we're going to clear fractions. So let's write it out. So we're going to have 1 over 1 plus x squared minus 1 over tan inverse of x plus x over 1 plus x squared. And the reason I'm going to do the following, I'm going to multiply top and bottom by 1 plus x squared, is it simplifies the problem, because we might have to do L'Hopital's again on this. So let's see what happens. Oh, okay, we'll stick with this color. Okay, we're getting, therefore, it's equal to lim, x approaches 0 from the plus, and we're getting upstairs 1, ready? He comes here, hits a 1, minus this, 1 plus x squared, okay. And downstairs we're getting 1 plus x squared times tan inverse x plus x. All right, clean it up a little, Weber. Okay, so it's equal to lim. Oh my goodness, some of these take a while, as you're seeing here now. 1 minus 1 is 0, but we have a minus x squared. Okay, fine. I see light at the end of the tunnel somehow. And then we got 1 plus x squared times tan inverse of x plus x. I should have practiced this before the video. But what we're finding is you're going to get 0 here, and you are going to get 0 and 0. It's going to be 0 again. So I think we're going to have to do L'Hopital again. Hey, can I stop this video? No? Okay. So it's equal to lim as x approaches 0 from the plus. Oh my gosh, this, I took it from the book. This guy, it's going to go forever. Watch. I'm going to derive the top, minus 2x. Okay, derive the bottom. Are you kidding? It's going to be 2x tan inverse of x, and then plus 1 plus x squared times 1 over 1 plus x squared, and then plus 1. Oh my glory. Let's clean it up. Lim x approaches 0 from the plus, minus 2x downstairs, 2x tan inverse of x, look at this, plus 1 is plus 2. Okay? You think I'm insane, but I have to tell you we have the answer, because whenever the top or the bottom turns into not 0 or not infinity, you're done. Because look, if we plug in 0, now we got minus 2 times 0. Okay, you're right, the top is 0. But look at the bottom, it's 2 times 0 tan inverse of 0. All of that is 0. You're right, but look, plus 2, plus 2. Answer, 0 over 2 is, wait for it, 0. For all that to figure out the limit was 0. And that's how it goes with L'Hopital. Some of these problems are insane. It's weird because you're going, in this case, we had infinity minus infinity. Anyone would say, I think it's 0. You were right this time, but it doesn't always happen. Maybe not the best one. This one's pretty crazy too. I don't know how long the video is. I bet you want to see me do it though, huh? This one, when you plug in infinity, is you've got 1 plus a over infinity, and then b times infinity. And inside there, this is, of course, 0 from the previous lecture. So we're left with 1 to the infinity power, which you'd go, oh, it must be 1. No, it's not, actually. You got a big surprise coming. So what do you do to make it look like L'Hopital? You're not going to like it, but let's do it anyway. We're going to take a look at, the natural log. This is a trick. If we look at the natural log and find that limit, then we take e to that limit and get your answer. So I'm taking 1 plus a over x, and bx is the power. Here comes a property of logs. That power can come down. So it's going to be bx natural log 1 plus a over x. You are in the army now, as they say. So we'll take the limit of that, thank you. The lim, as x approaches what? Infinity. Of bx ln of 1 plus a over x. Turns out to be infinity. Natural log, see what's happening? He turns to 0 again. Infinity, natural log of 1 times 0. Oh my gosh, are you kidding? It's one of those again. Yeah, it is. So we'll say, more trickery, lim, as x approaches infinity. Remember what I did last time? We're going to send that x downstairs. I think the b should just stay where it is. So we have b natural log of 1 plus a over x over 1 over x. Okay, now this guy is going to 0 over 0. You can verify that. So here comes L'Hopital one more time on a tough problem. And this is equal to lim as x approaches infinity. Derive the top, b times 1 over 1 plus a over x. And then deriving that, you get a minus a over x squared. Now, you're going to have to verify that because I'm trying to end this video. And downstairs is a minus 1 over x squared. We are now allowed to cancel those x squareds, cancel those negatives, and put the a and the b out of the way. In fact, you can take a times b all the way outside. It's just a number, time the lim as x approaches infinity of 1 over 1 plus a over x. Okay? Now you take the limit. I know it's crazy. And as x goes to infinity, this guy goes to 0 finally. And we've got a times b times 1, or ab. Yay, that's the limit. No, it's not. Remember at the beginning, we took the natural log. So our actual limit, I'll write this out. The limit as x approaches infinity of 1 plus a over x to the bx power is equal to e to the ab. And that's all she wrote. Okay. That's a lot. Those are a lot of good examples. You get to see them and keep them and look them over again, ask questions. So obviously I want to end this video here. It's a lengthy one this time. So I'll see you at the next one.